So everyone listen here. This is experiment number 2A, in which we have to go for simulation of a broadside array using CAD FEKO. And we know that an array is a device, or we can say that an antenna array is a group of radiators whose current are different and amplitudes and different phases. Means whenever we have to provide input to that array, we have to provide having with different amplitude and different phases. So an array is set of similar antennas, like you can go for combining number of dipole antennas, then it is treated as a dipole array. Similarly, you can combine different horn antennas, then it is a horn antenna array. So there are types of array, like there is a broadside array, Endfire array, and binomial as well as Chebyshev array. So in today's practical, we had to go for designing an broadside, Endfire, and binomial array. So whenever we go for a broadside array, arrangement of elements in an array, or in case of broadside array is like this. Means elements are arranged in a parallel manner to each other, and when we obtain the radiation pattern, so you are obtaining an radiation pattern, a bidirectional radiation pattern is obtained, and there are certain side lobes are present for that radiation pattern. Means there are two major lobes are present, and some more side lobes are present when we see the 3D radiation pattern of that particular broadside array. So whenever we have to design an array, then certain parameters we are needed, like what is the spacing between two elements and how many number of elements present in that array, as well as which type of current and which type of input you are providing. Means if the amplitude is uniform, or the amplitude is varying, or the particular phase is uniform, or it should be changing, and so on. According to that, there are types of arrays. So first we will go for this broadside array, and this is formula for calculation of array factor, like it is sine of n psi by 2 divided by n multiplied by sine of psi by 2. Here n indicate number of elements present in that array. But all these are theoretical part. What we are interested more in procedure for designing an array using CAD FEKO. So there are certain steps to be followed for designing an array using CAD FEKO. So first one is you have to define the variable which are used to be in that particular design, and by using a tab like define variable, you can use that. Then second step is you have to go for setting the model units according to the given problem statement. So either it is in centimeter or millimeter, you can change it. Then third step is you have to create a geometry of antenna according to the problem statement. Means whatever provide which antenna you have to design, you have to go for designing by selecting a proper geometry. Then you have to go for defining respective port to the geometry, then applying excitation to that geometry, and finally you have to set the operating frequency of that array also. And after that you have to add some requests, like there is a far field request and near field request. You can go for that, and which parameter you have to find, according to that you have to go for setting the request. If you want to go for radiation pattern, then you have to set far field request. Then after setting request, next step in this procedure is you can go for meshing the geometry. So geometry is divided in number of triangles with the help of meshing. You just have to provide a radius of that wire useful for meshing. And then after meshing, you have to validate the geometry by using CEM validate tab under sol oblique run. So by using that, you can validate, means all steps are uh, done properly, then it shows a proper validation. Otherwise, there is an error present in this validation. And after successful validation, you can run a CAD FEKO. And for obtaining result after running CAD FEKO, you can get result in post FEKO. And in post FEKO, you obtain results like a 2D radiation pattern, 3D radiation pattern, gain, directivity, return loss, VSWR, beam width, and efficiency of antenna. All these parameters you can obtain in post FEKO. So these are the steps which you have to follow for designing an antenna using uh, CAD FEKO. First, we have to design a broadside array, but we require a problem statement, means what we have to design. So see here, this is the problem statement for designing an broadside array. So here the problem statement is design a two element broadside array antenna, means here number of element present in that array is 2, working at a frequency of 300 megahertz, means the working frequency of that antenna is 300 megahertz, and the length of each element is lambda by 2, means here simply a half wavelength dipole. Lambda by 2 means half wavelength dipole is used as an element in this array, and the spacing between individual element of an antenna is zero point 0.7 multiplied by lambda, means if there are two elements array, then the space between these two elements is given by zero point 0.7 multiplied by lambda, and the radius of wire used for meshing is equal to 2 millimeter. So when we see this problem statement, there are certain things are already given, like a number of element equal to 2, then operating frequency is equal to 300 megahertz, then the dipole is used, lambda by 2 dipole is used as an element, and the spacing between individual element is zero point 0.7 multiplied by lambda. Now we have these data, and according to this data we have to go for designing an broadside array using a CAD FEKO. So I will show you one video how to go for designing an array using broadside or using CAD FEKO. So see here, this is an CAD FEKO environment. What we do first, first step is we have to add the variable. So for adding variable, you can go to the construct, and these are different options available in this CAD FEKO, like construct, transform, and source load, and so on. For adding variable, we can go to the add variable, and when you click on add variable, then a tab like create variable is used. So we are adding variable for frequency, so name of variable is f, and now I have to put value of that frequency, and we know that the value of frequency is equal to 300 megahertz. So it is, I have to put here like 300 E6, and when I evaluate and then add. Similarly, I will go for another variable for lambda, so LA, and there is a formula for calculation of lambda like C0 by F. So it is calculated and it is evaluated and added. And finally, I will go for one more variable, that is R, so which is equal to 2E minus 3, that is the meshing wire radius. So it is 2 millimeters, and then I will evaluate and add. So in this way, I had added variables like frequency, then lambda, and um, R. So F is 300 megahertz, lambda is C0 by F, and R equal to 2 millimeter. Then I have to create a geometry. So for creating geometry, I will select line under construct tab. And whenever I see this line, so there are three axes, U, V, and N. And again, there is a start point and end point. If the length of dipole is lambda by 2, so I have to vary it is from minus lambda by 4 to plus lambda by 4, so that the total length is lambda by 2. So I am I am varying axis n here from minus lambda by 4 to plus lambda by 4. Now I am varying u axis from minus lambda by 4 to plus lambda by 4, means starting point minus lambda by 4, ending point plus lambda by 4, all other 0. And now I'm showing also for what we do with varying v axis. UVN is like an XYZ axis. U indicate X, V indicate Y, and N indicate Z axis. So here Y axis is varying from minus lambda by 4 to plus lambda by 4. So the total length is equal to lambda by 2. So I am giving name as a D1. So under model, it should be comes like a D1. Then I have a two element array. So I have to go for another line, and again I am varying here v axis from minus lambda by 4 to plus lambda by 4. You note that we already define a variable la for lambda, so minus la by 4 to plus la by 4, and all other values are equal to 0. This u value also become 0. only I have to vary v from minus lambda by 4 to plus lambda by 4. And now I will give you a label, and here u value is spacing. So spacing is 0.7 multiplied by lambda. It is given in problem statement. So u value is equal to 0.7 by lambda, and I am adding label as a d2. So I have created two lines, d1 and d2, and it should be shown like this here. So first line is d1 and second line is d2. Now I will put port on that D1. So I will click on wire 1, go to the source load and observe on wire port. So wire port is at middle position. So I will add this. And after same procedure, I have to repeat for this D2 also. But what do I have to do? I have to click on wire 2, wire 4, and then go to the source oblique load and then middle position of port and then add. And after that, I have to go for adding excitation also, but before that frequency should be set by adding variable f for that, and it is equal to 300. So that is equal to 300 megahertz. So see here, the frequency should be shown here, like frequency equal to 300 megahertz. We already discussed or already defined a variable f for that. Now I have to add excitation. So I will go to the source load, and voltage source is added as the excitation for port 1 as well as for port 2. So an excitation, voltage source 1 and voltage source 2 are added as shown in here. And after that I have to select D1 and D2, and I have to combine geometry. So I will go for construct and union option. So now it is a single geometry. And after that I have to mesh this design by using create mesh, and here wire segment radius is variable r, which we had declared. So the element of dipole are divided in number of cylinders by processing of meshing process. And finally I have to go for this port 1 and port 2, and here magnitude and phase is unchanged, like 1 and 0. Now I will go for adding request. So far field request. So I will go for this 3D pattern request, and under request tab, it should be shown like far field request is spread. And then now I validate design by pressing CEM validate. If all things are green, means it is properly validate. And then I have to run the FEKO by pressing FEKO solver. But before running, I have to save this design. So I will create a new folder on desktop, and I am giving some name for that. Say it should be Broadside. And now it is running. And when it is 100% running, I have to obtain the result in post FEKO. So I will click on post FEKO. So a separate tab is open having name as a post FEKO. And in post FEKO, now geometry should be shown here. So I will go for far field request. So I will click on far field and far field 1. So this indicates a 3D radiation pattern. Similarly, this is a 2D radiation pattern for this particular antenna. But this radiation pattern is only half one. So what I have to do, I have to change the far field request again. But for that purpose, I have to go in this particular CAD FEKO. This is a 3D radiation pattern. Here you show a total gain of 5.4, but the gain is measured in decibel. So but it is not in dB. We have to check the dB for measurement of gain. This radiation pattern is a 2D one, but it is not in what we can say that half radiation pattern only. So for doing that, what we have to do, we have to again go to the CAD FEKO. So I don't want to save here. So I will discard this. And then I'm go to the post FEKO, and here I will change the request. Like here theta varies from 0 to 180, so I will change to like 0 to 360. Phi varies from 0 to 360 with an increment of 5 degree. And now I'm changing some doing some changes. So again I am running this FEKO solver after changing the far field request. So I'm getting again go to the post FEKO, same geometry should be present over there. And this is a 3D radiation pattern you had obtained for this particular broadside array. It's showing two major lobes and some side lobes are present. And when I click on dB, so here total gain in dB is equal to 10 dB, and this indicates polar pattern or a 2D radiation pattern with some side lobes and two major lobes also. On this, you can calculate beam width, like half power beam width and first null beam width, by going to measure and then under beam width option, half power beam width and first null beam width. You can calculate using that. So here first null beam width is equal to 315 degree. You are getting from that. So by changing parameters, like here it indicate total gain. So you change the parameters from gain to directivity or electric field, then it shows a electric field value. So it is total electric field, which is equal to 10, but it is not in dB. So you have to uncheck this dB. So this is about a broadside array. So what we do here in broadside array, we will go for designing a broadside array using this particular CAD FEKO. So frequency is equal to 300 megahertz, and the length of this spacing between individual element is 0.7 lambda. Now this is about the broadside. Now we have to, what we have to do, we have to change the same design for Endfire. So what, for that purpose, we have to go for finding difference between broadside and Endfire. We know that there is only one difference between broadside and Endfire array, is that there is a progressive phase shift. The progressive phase shift is only present in case of this particular Endfire array, which is not present in broadside array. So what we have to do, we have to only change the phase shift for the second element. Then you can say that the broadside array is converted into Endfire one. So I will show you video how to go for changing that. So see here, this is an video for Endfire array. Same design I'm using here, like we had designing a 2 element broadside array, but we want to convert that into Endfire. So for port number 1, the phase is 0 degree under excitation, but here it is equal to 180 degree because there is a progressive phase shift is present over there. And now I will save this, and again I have to mesh this design, and again I have to run that CAD FEKO by using option like sol/run. You can hide that request also by using show hide button. So sol/run, and then first I have to validate this design after change, and then I have to go for running by pressing FEKO solver. And now I have to obtain the result, which is in post FEKO. So the same geometry should be shown here. Again, I have to go to far field, then far field 1. But now it is for Endfire array. So the radiation pattern is changing here. It should be indicated 3D radiation pattern because we are using a progressive phase shift here. First element having 0 degree phase shift, but second element having 360 degree phase shift. Now I will go for this directivity also and gain in decibel. So it indicates the value of gain, that is 5 dBi or dB. For the I indicate isotropic. Then I will go for polar, then far field 1. So this is a polar plot of Endfire 2 element Endfire array. Now I will calculate half power beam width as a 138 degree, and first null beam width as a 135 degree or by using this 2D radiation pattern. And I will calculate efficiency also by clicking out file and searching phrase for efficiency. So it indicates efficiency of the antenna is equal to 100% because we are using a lossless material here. So no losses are present. So the efficiency is equal to 100%. And by changing to the electric field, you are getting this electric field value in volt, that is 1.12 volt. So by only changing the what we can say that phase shift, first element having 0 degree phase shift and second element having 180 phase shift, we can convert an broadside array into Endfire array. And according to that, the radiation pattern is also changing, and then all other parameters are also changing. Similarly, the third array is what we can say that binomial array. So if I want to convert a broadside array into binomial, what change I have to do? First thing is that the spacing between individual element. For broadside in problem statement, it is shown that the spacing is zero point 0.7 multiplied by lambda, but for binomial array, it is needed that the spacing is equal to zero point 0.5 multiplied by lambda, or it is lambda by 2. And then there is another condition is that the amplitude is according to Pascal's triangles. Here, this is the Pascal's triangle. Here, M indicate number of element. So if the number of element is 1, then amplitude is equal to 1. If number of element is equal to 2, then it is 1 and 1. If number of element is equal to 3, then it is 1, 2, 1. If number of element is equal to 4, then it is 1, 3, 3, 1. And similarly, if there are 5 number of element, then it is 1 plus 1, 4, 6, 4, 1, and so on. So what we have to do is we have to change the amplitude and we have to change the spacing in case of this binomial array. If I want to convert broadside array into binomial one. And one more advantage of binomial array is that there are no side lobes are present. When we discuss about radiation pattern of Endfire and broadside array, side lobes are present, but in binomial array, there are no side lobes. So again, I will show you one video how to go for designing that binomial array. So the same design for broadside array I'm using here. What I have to change is I have to only change the spacing, that is from 0.7 lambda. I have to change to 0.5 lambda, as well as amplitude is for two element, it is 1 and 1. So I will go for changing the spacing. So for changing spacing, I will click on this D1 and D2. I will click on D1 first. So I have to change here the spacing. So spacing is only present at D2. So I will change from 0.7 lambda to 0.5 lambda. 0.5 lambda means it is lambda by 2. Then I will go for pressing OK. And now I have to change the meshing again. I have to do meshing again. And again I have to validate and run. So after running, you have to obtain result in post FEKO. Again, same geometry should be present over here, which is run in CAD FEKO. And I will go to far field 1. Now you see here, there are no side lobes are present. Only two major lobes are present over here. So side lobes are reduced in case of this binomial array. This is advantage of binomial array. No side lobes are present in binomial array. I will show you radiation polar pattern also. That is a 2D radiation pattern. So this is a 2D radiation pattern of a broadside, binomial array. And you can measure half power beam width, that is 120 degree, personal beam width, that is 90 degree on this polar pattern. And here everyone listen. there is no side lobes are present over here. So this is advantage of binomial array. So side lobes are not present. So you can calculate gain here 5 dB for this binomial array.